This call is now being recorded.
As I said, we have a rough surface here. So rough surface is telling us we have friction, right? So that means we've got a force that is trying to pull this box the opposite way. So this would be our friction. This is friction. This is applied force. So the applied force is doing positive work. Then the frictional force is doing negative work, right? So the reason these are doing opposite works because friction is pulling to the other side and the applied force is also pulling to the other side. So they are doing opposite work. So in this box, we also have other forces. We've got our box here. We've got our friction that comes as a rough surface. Then we're going to have our forces here. We're going to have our applied force. Then we're going to have our friction here. Then we're going to have our normal force. Then we have our weight. Okay. So all these forces are doing work. Just that it's not all the work being done that you're going to see. Applied force, let me just say FA instead. Then here, this is friction, FK. This is normal force, Fn. This is Fg, which is our weight. Fg is equals to mg, mass times our gravitational acceleration. Okay. So let's move. So remember, our work is equals to force, our displacement here, cos theta, right? So work that is going to be done here, because this is our surface. Between our surface and this force FA, the angle theta is 0. So we don't have an angle. And also for FK, same thing. But now for Fn, we've got theta equals to 90 degrees. Same thing for Fg, we've got theta equals to 90 degrees. Where is this 90 coming from? Look. So let me extend just a bit here. If you can see this surface here and this force, they are perpendicular to each other. This surface and the force, they are perpendicular to each other. Same applies to the normal force. Hence, we have our angles as 90 degrees, right? So if we can take this, then say cos 90 degrees, what would you get? Anyone? I will wait with you. I want to know what is cos 90. You don't have calculators or we don't know. Okay, seems like people don't know what is cos 90. It's going to be a difficult journey, but cool. It's equal to 0. Hence, we are saying the work done by the force of gravity and the work done by normal force as 0. So if we were to calculate work done by the normal force, would say F normal, our displacement, and then cos 90. All this will be multiplied by 0, hence would have a 0. Same applies to F done, work done by gravity. You would have the same thing as equals to 0. Hence, we always ignore this. Unless the box is not moving horizontal, but is moving vertical, then you'd have a different thing in that case. Okay. Do we understand? If you don't understand, please shout. And if you understand, please put a thumbs up so that we can carry on. Guys, can you hear me or you can't hear me? Okay, maybe it's me who can't hear you. Coolies, let's move. So now let me make an example for you. Example 1, we've got a box here. Our 10 kg box. There's a force applied. Here. This is 100 newtons. But now this is on a flat surface, right? In this case, what would be the work done by our applied force? So say here you have 60 degrees, the angle between the surface and your force. So in this case, we already know what our work is. So work is equal to force times displacement. So displacement is going to be something like this, cos theta. So if this box moves 5 meters, then work is done. As long as it doesn't move, there's no work done because we have not covered any displacement here. So we need it to move, even if it's an inch, as long as it moves. So if our box decides to move 5 meters, we can simply substitute here times 5 meters times cos 60. 60 being the angle between the surface and this angle and the force. So that would be 500 times 1/2. Then you would have your answer. What is force? What is work done on this force or by this force? Anyone? You are so quiet, guys. Do you understand what is happening or you don't? Okay, coolies. Gonna have 250 Newton dot meter, which is joules. But then if we have, or let's say they ask us, what is our work net? But now, if they want work net, you would have something like, let's say F net, our displacement cos theta, right? because the displacement would still be the same for every force that is acting on this box here. So if they want F net, that means we now need to add the force friction here, the work done by friction. So if, let's say, friction is equals to, let's say, Fk is equals to 30 newtons, we can simply calculate work done by friction. Work done by friction would be equals to 30 times 5, because the box has moved 5 meters, cos theta, right? So since this is 0, you can say it's cos 0. So then it's going to give you the answer. So why are we saying cos 0 in this case? This is because the angle between friction and the surface is 0. That's why we're saying cos 0. So here you'd have 150 joules for your Fk, but in opposite direction. This is gonna be negative because this is negative work, right? So if we get here now, we can calculate F net. F net is gonna be force, which is the applied force, plus minus Fk, which is your friction. We already know the force is 100. We've got friction here as 30. This is minus 30. So here you can have 70 newtons, which is your F net, right? So I want to show you in two ways. Here you've got two ways. You've got work done by friction and you've got work done by the force. So if we were to use that and say work net equals to work done by force applied plus minus work done by friction, would have something like this. So that means it's going to be equals to work done by force is going to be 250 plus minus, this is minus 150. Okay, so this case you'll be left with 100 joule. This is your work net. So what if you use this instead? What if you decide to say work net is equals to F net times cos theta, right? So now here, this is wrong. Why is it wrong? Because it's at an angle. So you can't take 100 at an angle and put it against 30, which is at a 0 angle, right? So that means this work net here, net force, you'd have to change it. So you'd have to use X component, the one that I was showing you here, this one, right? So that means we are going to have to calculate Fx. So Fx would be F cos theta, right? Equals to 100 cos 60, right? Then equals to, what is that? Should be something like 50 newtons. Okay, now we have 50 and we have our friction. F net then equals to this Fx here plus minus Fk, which is going to be 50 plus, where's friction? 30, which is minus 30. Then equals to how much? 20 newtons, right? Can you hear me? So in this case, we said F net equals to F net times X cos theta. So now we would have your F net, which is 20. The distance would remain 5, which is 5 cos. But now we no longer have theta because we have components, right? So that means we have 0 here. Then you would end up with work being 100 joules, like this, work net, right? So let's carry on and check out other cool stuff from work, right? We have something called the work theorem. Okay, work theorem. So the work theorem says something, right? Says the total work or net work. Net work done on an object is equals to the change in the object's kinetic energy. Right? So what is kinetic energy? Let's start there. So this is kinetic energy. Kinetic energy is equal to 1/2 mass times speed of velocity. Right? This is our kinetic energy. So what they are saying here, they are telling us that work net is equals to the change. This is change. This is change of kinetic energy. What they are telling us is that initial or final kinetic energy minus initial kinetic energy is equals to work net. That's what they are saying here. All right. Do you understand?
Yes.
Cool it. Thank you. So then we also have a network that is done by non-conservative forces. So that work would be a bit different from this. Okay. So for let me write it here. Conservative forces would have work net being equals to the change in kinetic energy, but now we introduce the potential energy. So this is the gravitational potential energy, this one here. Sometimes You can see it like this. This is your potential energy here, right? This is your kinetic energy here. Okay, if I can expand this for you, you would have something like work net equals to kinetic energy final, kinetic energy initial plus U final minus U initial. Okay, for non-conservative forces. So those are the forces like your friction and so on. Because now it depends on a path, right? We know what are conservative forces. Okay, we're gonna see them. Don't worry. Then we have the principle of conservation of mechanical energy. Okay, so let me write it on a new page. So let me use a different pen. Conservation of mechanical right? So conservation. So that means remain the same. If you're conserving something, it's more like you are saving it. If I give you 10 rand today, even tomorrow, you're gonna come back with 10 rand. If I give you 10 rand while you're at school, then you come back at home with 10 rand also. Right? So you have saved that 10 rand. So what this is saying to us is the total mechanical energy in an isolated system remains the same, right? So let me put it like this. So total mechanical energy in an isolated system. In an isolated system. This is very important. What is isolated system? That means we are not having anything. We're not having anything coming into our home. Right? So there is no force from outside that is going to come inside our system, and nothing from our system is going to leave and go outside. Right? So this is isolated system. So it's like, hey, let me just finish this. An isolated system remains, okay, remains constant. Okay, so if we had a box like this, and inside this box we have this box and this box and this box. This is an isolated system if you look at it from this point of view here. This is isolated. It will not allow anything to go inside it or allow anything to get outside of it. Everything remains the same, right? So what is mechanical energy? So what this is telling us is that the mechanical energy, let's say mechanical energy at the top is going to be equal to the mechanical energy at the bottom. So let's say we have a path or a mountain like this, right? This is U here. So this mountain, this is the ground. This is the ground. So we've got the height here, which is H. You are a person, so you must have a mass, which is 90 kg. K, right? So now we are here. What this is telling us that the mechanical energy here at the top is going to be equals to the mechanical here at the bottom. How do I then represent this to you? What they are telling me is that mechanical energy mech is equals to kinetic energy plus potential energy, right? So that means this kinetic energy plus potential at the top here is gonna be equals to the one at the bottom here, right? This is what they are telling me. And remember, I've already shown you that is equals to 1 over 2 mv squared, and then u p is equals to mgh. This is the h here, right? The m, this is the m. What is the g? The g is 9.8 meters per second squared. Do you know what this is? Does anyone know? No one knows. Cool. This is the gravitational acceleration. Okay. So talking helps you to understand better. It makes things easier for you. And then you can ask me if you have any question. Don't just suffer in silence. It won't help you. You have to talk so that we can help you and we can see the gaps that we need to fill. Okay. Coolies. Let's carry on, good people. Jesus, so there's still people who can't join. Okay, let's pause again for a moment. Maybe try digesting what we are going through.